We were in the middle of talking about the spread of a disease model. Remember in section 1.3, what we're going through is looking at several different actual applications where we would derive a differential equation to model something happening in the real world. And we've looked at population dynamics and radioactive decay, which are both actually the same model. We did look at Newton's law of cooling. And then now we're going to talk about spread of disease. We're going to also look at mixtures today, falling objects with and without air resistance. And that'll be all we cover for 1.3. We'll have a few other models we'll pick up throughout the semester as we start looking at types of differential equations that fit those. But this is where we got to last time on the spread of disease. We're doing a very simplistic model where we just have two classes. We have the category of the population that has contracted the disease, and then we have the number that are uninfected. And the assumption that we're going to make that helps us derive a differential equation is that the rate of people contracting the disease, that is, the rate of growth of X, is jointly proportional to X and Y. That is, the more total people there are in the population, you would expect more to contract the disease. If you have more people with the disease, if X goes up, you would expect the number or the rate to grow. If even Y goes up, you would expect the rate to grow because there'd be more people available to or susceptible to becoming infected. And so this was the model right here, the dx dt is equal to kxy. And that just comes from the concept of jointly proportional can be modeled as a product or proportional to the product of xy. Now what's a little bit of a downside to this right now, you can see a flaw in this, is that I've got actually how many dependent variables in that model? Two. I've got x and y, and then I've got one independent. Okay. Now typically what you're going to need in order to solve this thing uniquely, or at least to find a general solution to a system like this, is you'd need a differential equation for x and for y. It is, you need two equations for the two dependent variables that you have, and we only have one. So one refinement of this that helps us get rid of that problem is to assume a certain sized population, not an infinitely sized population. So let's think of it this way. Let's assume a fixed size community of n, and then what we're going to do is add one infected person or individual to the population. Okay, so we're going to assume a fixed size community of n with one infected individual added. So notice what that would mean then is that x plus y, the total amount of people, total number of people in the population, is now that n plus one new individual. And now that creates a dependency of either x or y on the other variable. So what we can do to reduce this down to a system of just one dependent variable is to solve that, right? So y will always be then n plus 1 minus x. Now, if that is the case, then I can just take that and substitute it up into that equation, which gives me actually a full initial value problem, because I have now dx dt is equal to k times x times now y, which is n plus 1 minus x. And what's the initial condition? What do we start with for the value of x? What is x at the starting time? Based on this statement right here, the refinement. 1. One infected individual, right? So I started with introducing one person in, so that's going to be 1. By the way, if you put in 0, you should expect that the solution should just be the 0 solution, right? If you have a completely uninfected population, and you add a person who's uninfected, population shouldn't become infected at all, right? It should stay constant 0. But now when you introduce 1, what should happen? And we would find that by solving this differential equation here, which we don't know how to do yet, but we will, okay? Yeah, I know, I'm holding you in suspense. It's like reading a good Stephen King novel. You know, all the pieces are being put together, but you don't know what's going to happen next. So that's what a model for a spread of disease might look like. Okay, so the kinds of questions you might have to answer in your homework on 1.3 would be to have to find like the value of K under certain given information. Like if I told you that the rate of growth of the disease was 3 people per day on the 3rd day. That's enough information, and the population is, say, 100 people. That tells you N, that tells you the rate, and that tells you an X to plug in, leaving only K to be found. So the types of questions I'm going to ask in this section about this particular model, or even the previous model on cooling, is mostly an algebra question where you just have to plug in what you do know and solve for the thing that you don't know. I'm not being able, I don't have you don't have the skills yet to answer a lot of differential equation questions. Now the next 2 or 3 models I'm going to give you, you actually will have to build the differential equation based on the parameters in the model with a little bit more work going into it. But these are pretty static models. It's always going to be this way if you make these assumptions. The same thing's true on the population dynamics. You may have to find the K, but it's always going to be dP dt equals Kp. That's the Malthusian model. That's the simplified model we're looking at this point. Okay? All right, so that's spread of disease. Mixtures, I think, a little bit more fun. What we're going to be talking about with mixtures, the simplest way to think of it is to think of like a giant tank of some solution where you have coming into the tank some mixture, maybe like a brine or a saltwater mix. But as I'll illustrate with some other examples later on, it can be all kinds of different things. It doesn't necessarily have to be water with salt mixed in. It could be just air with a biological contaminant mixed in, being piped into a room through an HVAC system. In fact, I worked on a project where we did that exact kind of model, and the differential equation that we used to solve that is this exact one right here.
What kind of model did you murder people?
I worked for the Army on developing real-time training simulations in which biological contaminants had been introduced into a closed HVAC system, and they had to walk around the building with a little meter in their hand, and we had to change the model based on whether they opened doors and how the flow moved between the rooms. So my part was solving the DE. I was never in the phase of actually implementing the training. I was just tying in a DE model into a given simulation, and then they took it and did whatever with it. So I don't know. The other guy I was working with, he was in charge of taking the blueprints and turning them into the 3-dimensional environment in which you would move through with some gaming simulation. I don't know if we were using what the game engine we were using, but that was his job, and I was just tying in DE models into a little handheld meter that you could turn on, and it would tell you how concentrated it was, and you know, if it got high enough, you were dead, you lost. So. Okay, so we've got something being piped in. We're going to model the amount of, let's say for now, I'm going to put in quotes, salt. That's whatever the substance is at time t. So say this thing has a particular volume V, and we're pumping it at some particular flow rate and some particular concentration, and then we're piping out at some flow rate. The kind of assumption we're going to make here is, well, first of all, that the rate of change of salt in here is however much salt is coming in, how fast it's coming in, minus how fast it's going out. So if we're adding salt at like 3 pounds per minute, and the salt is leaving at some rate, we're going to try to figure out then how much salt is in there at any given time t. The simplest model would assume that the flow rate up here at the top equals the flow rate down here at the bottom, because if the flow rate, that is how much actual volume is coming in, like 2 pounds, not 2 pounds, but 2 gallons per minute is coming in, 2 gallons per minute going out. If there's a difference between those two, then either you're going to drain the tank or you're going to overfill the tank, right? The volume of the tank is going to change. One of your problems in the homework has you take into consideration whenever the flow rates are different. But for now, let's assume those flow rates are the same. So based on this assumption that I've got right here, I'm going to say that the rate of change of salt is the rate in minus the rate out. Now, typically what you will know is how fast the water is coming in. That is, what is the volume per unit time coming in. And you'll know the concentration coming in. That's how much amount of salt per unit volume. So the rate, in either case, rate in or rate out, is always going to be whatever the concentration is, which is typically a unit like pounds per gallon, right? Weight per unit volume. So you have 3 pounds per gallon of salt. That's actually a lot. You have 3 pounds per 100 gallons of salt. I don't know if you can dissolve that much salt into 1 gallon, but you'll have something that makes sense, okay? Times the flow rate. It's what I'm calling how fast the water is actually going. That'd be like gallons per minute. So notice that would give you a unit of pounds per minute, which is exactly what we're looking for. It's how fast the amount of salt is changing per unit time. That's what a rate would mean. But that's true for rate in and rate out. But what you got to notice is whenever this thing comes in, another assumption that I didn't write here that we're going to have to make is we need to assume that this thing is thoroughly mixed at any given time t, which is a poor, non-realistic assumption, but it's necessary for us to be able to solve this simply. Because if you start talking about how it swirls and vortexes throughout this tank whenever you drop in salt and you stir it up, you know, there'll be some higher concentrations in one part versus another. Modeling what happens inside of a fluid as you move through it is extremely complicated. Computational fluid dynamics is an enormously complicated field of study, and beyond the scope of this class and beyond the scope of any graduate class that I took. I mean, people get PhDs in computational fluid dynamics alone. So we're not going to talk about that. We're going to make it simple and assume once we put it in, let's keep this thing stirring, and a close approximation of what's going on is it's thoroughly mixed. It's equally distributed all the way throughout, okay? So make a note down here. We'll also assume the tank is thoroughly mixed at all times. And just one other side note, stick in here. In general, concentration, you should know this already, but I'm going to write it down anyways, is amount over volume. Okay, that would be A at time t divided by the volume of the tank. That's what you're going to need to find the concentration going out. You'll have a fixed concentration coming in, but going out, it'll be variable because the tank is changing the amount of salt over time. So the concentration in the tank is changing over time. That's this A of T over V. Okay, with that, now we can do an actual example. All right. So let's say we've got a tank where, and I'm going to draw a picture over here, and I'm going to actually make it even simpler because I'm not very good with this little tablet over here. Coming in and going out. Coming in, we have 3 gallons per minute. Going out, we have 3 gallons per minute, which means the volume is going to stay the same. We're told that the volume is 300 gallons. We're also told that the brine concentration that's coming in is 2 pounds per gallon. So that is sufficient information for us to build a differential equation that would model what's happening to the amount of salt in that tank over time. Okay? So let's think about it. dA dt is going to be rate in minus rate out. So let's talk about rate in. Remember, rate is concentration times flow rate. So what's the rate coming in?
6.
Just 6, a constant 6 pounds per minute coming in. Easy, easy peasy. And you got that again from doing 3 pounds per minute times 2 pounds per gallon. The rate out,
3 gallons per minute.
it's 3 gallons per minute, but that's just the flow rate. What's the actual rate of salt going out? So you've got to multiply the flow rate times the concentration of what's actually in the tank at that time. Time t.
So times, should be 6 too.
No, because the 6 is, I mean, if we plug in, say, a 2 pounds per gallon, that's what's coming in. Now, we may start with a completely pure water tank that has no salt in it, right? So if the water's coming in at 2 pounds per gallon, we won't have that concentration instantly at the beginning.
So times rate in times time divided by volume of the tank minus rate out. Or
It's a lot simpler than that. You're making it too complicated. Because we know, I mean, at least we have a variable that represents the amount of salt at time t. Right? That's what A is. Right? That's what we set up here. Get my scroll bar. Hey, looky there. That's a neat little tool. All right, so up here, I've got amount of salt at time t. And I know then, and this is why I wrote this note right here. The concentration at time t is A over the volume. So A is unknown. What's the volume of the tank?
300.
300. So the rate out is going to be 3 gallons per minute. That's the flow times the concentration of the salt, which is however much salt is in there divided by how much liquid is in there, divided by the volume, A over V. That gives me A over 100, or 1/100ths times A. I just canceled the 3 with the 300.
Oh, okay.
Right.
Is that A of T?
Yes, yes. Which, because I know it's the dependent variable, I will often just leave off the of t, just for simplicity's sake. I assume from the beginning that A is a function of t. Just like when we write y's and x's, when we know that the x is the independent variable and y is the dependent variable, I don't always write y of x. I'll just write y and it's implied. So sometimes I'll switch back and forth. If I write it, it's because I need to emphasize the fact that it's dependent on t. But we should be able to identify that from the context. So now then, dA dt,
Is that pounds per gallon?
yes, just like the unit above would be. Pounds per minute. Because it's how
Right.
this concentration right in here, even though I didn't write it, would be whatever that A value is at a given time t is in pounds. 300 is in gallons, so that's pounds per gallon there. And when you multiply gallons per minute times pounds per gallon, you get pounds per minute. So both rate in and rate out will be in pounds per minute. So what I get then is rate in is 6, rate out is 1/100th of A. And if I could solve that differential equation, then that would give me a solution that models the amount of salt over time. But I also would set A of 0 equal to A naught, where that's the initial amount of salt. So this right here forms an initial value problem. So specifically down here, I would write that the IVP, if I know A naught is 1 pound per gallon, I got to do a little work to figure out what A of 0 is, but we'll do that. dA dt, the differential equation, is the 6 minus 1 over 100A. Now I got to know what is A of 0. So if I tell you that the initial value problem needs to be found and the initial concentration is 1 pound per gallon, how much salt is in this tank at the beginning? One pound, initial concentration, 1 pound per gallon.
How many gallons? How many gallons?
And there's 300 gallons, which means the amount would be 1 times 300, right?
Mm-hmm.
Which equals 300 pounds. So A of 0 is 300. Just keep in mind, what we're modeling is amount of salt, not concentration of salt. All right, so let's walk through this one more time, because you're going to do this a couple of times in your homework. When you want to find the rate in, it's just how fast the water's coming in times the concentration of that substance, salt in this case, coming in. So that generally is going to be a constant. Sometimes it's even 0. Like if, say I start with something that's got a contaminant in it, and then I pump in a bunch of pure water and pump it out at the same rate. We want to find out how long it takes for that level of that amount to drop. So in that kind of example, the flow rate would still be some constant, but the concentration would be 0. So that rate in could even be 0. In this case, it's 6, because we've got 3 pounds per minute, 2 pounds per gallon, so we get 6 pounds per minute. The rate out, because the rate out depends on the amount of salt which is changing, that's going to be where your variable typically shows up. It's how fast it's going out times the concentration at a given time, which is always the amount divided by the volume. A over the volume. So then simplify that. That's where you get 6 minus 1 over 100A. And then to get an initial condition, you remember you have to figure out how much salt is in there at that starting point. Not what the concentration is, but actually how many pounds of salt is in there.
If you did this for purification, like, wouldn't it technically, mathematically take infinite?
It would never go to 0. So what you really do, the kind of question you ask is, when does it fall below some acceptable limit, right? So if you're, say you work for the EPA and you've got a pollutant that's allowed to be at, 1 parts per billion, at what point in time does this particular procedure you've introduced get the level down to that?
Could you do it by moles and have it?
Uh-huh. I mean, units don't matter. I mean, the units are...
well, I mean, if you did it by moles, could you have to go down to 0 then?
Well, the way you're setting this model up, it's still going to be asymptotic, so it never actually reaches 0 in finite time in this particular model. Now, there may be ways, there are ways. There are other types of models, even discretized models, where instead of modeling the amount of a substance by a continuous variable, you model it by discrete values. But that's actually a whole different field of study from differential equations. They're called difference equations, where your output variables are discrete variables instead of continuous variables. So yes, it can be done. Usually the amount of work that goes into a difference equation is a whole lot more work than goes into a differential equation, and the difference between the two answers are so negligible that it's easier to use the differential equation to model it or even approximate it. All right, let's throw some things out of a plane, shall we?
Yes.
Falling bodies. I don't know why I couldn't just use the word objects. I have to throw in the word bodies for some reason. All right, so I'm going to model a body by this block here. Here's the ground down here. I'm going to start with this object right here, and I'm going to drop it. It's going to go down this way. Okay, let's say the initial height of this right here is s sub 0. So I'm going to let s of t be the height of falling object at time t. All right, so the assumptions are basically Newton's laws. Right? An object at rest tends to stay at rest, an object in motion tends to stay in motion, that the resultant force on an object is the sum of all the forces acting on that object, that the force is equal to mass times acceleration. So using the fact that, if s of t is the height, s prime of t would represent, not quite, first derivative of
Velocity.
position function is a velocity function or a speed, right?
Right.
Actually, velocity because it would have direction. And then s double prime of t would be acceleration. Not that it's relevant to this, but I always like the third derivative name. You know what the third derivative of a position function is, right?
Jerk.
Yep. The jerk function. All right, so s prime of t, s double prime of t. So what I'm going to use is basically this fact, that the force acting on an object can be summarized by the sum of all the forces acting on that object. And that resultant force will be equivalent to the mass times the acceleration of that object, or in our case, d squared s over dt squared, or the second derivative of s with respect to t. Shouldn't say squared. Okay? We'll also use the fact that acceleration due to gravity is a constant g. Now, depending on what textbook you read, it varies from one book to the other, and just one problem to the other in many examples of whether or not we orient this coordinate system the typical way, where up is positive and down is negative. There's plenty of examples where they just assume down is positive, so that as it's going downward, you're just going to expect everything to move downward, so we think of that as the positive direction. I'm going to do it both ways just to keep you on your toes and make sure you're paying attention to whether it tells you that positive is down or positive is up. You got to recognize that in the problem. So let's assume that this is oriented a typical way. Let's orient the coordinate system so up is positive. And when I do the falling bodies with air resistance, I'm going to do the same assumption. I actually get a different equation, slightly different. Well, my signs are different than what he has in the book, because this typically is the way that I've always done it. Okay, so let's just assume for falling bodies no air resistance. there's only one force acting on this thing, and that's gravity. Okay, so there is a force mg going downward, and it's negative because it's pointed down, acting onto that object. So your mass times acceleration, which is d 2s dt 2, would be equal to negative mg, right? You always set mass times acceleration equal to the sum of all the forces, and this is mass times acceleration. As a result, if you divide both sides by m, notice that the mass of the object actually has no bearing on the resultant equation. And if you had your calc-based physics already, this is old hat to you. You've seen this before. Okay, so there's your differential equation. Now, if you wanted to write this as an initial value problem, you need to have two initial conditions because it's a second order differential equation. So you'd need to set s of 0 equal to something and s prime of 0 equal to something. So in my drawing here, s of 0 is clearly s naught, because that's the height of the object at time 0, where I'm starting. Now, I didn't give you any information in the drawing, but you might have an initial velocity as well. You toss the object upwards, or even throw it downwards, or just release it from a standing still position. You'd need to know what the initial velocity was in order to solve this thing uniquely. So this is the initial height, and this is the initial velocity. Does that look familiar to you? Maybe not in this notation, but that's the idea behind what we use even in physics to get our formulas for dropping something from a particular height. Right. And it's easy to solve. I mean, this one's actually not even hard to solve. You don't need anything from differential equations to solve this because it's a standard integration problem. Notice the right-hand side is just a constant, so you can integrate both sides with respect to t, and then integrate it again with respect to t to get the actual s function. So all you have to do to solve this one is integrate both sides. But adding air resistance adds a little bit of a complication. So this is a refinement of that model. Questions before I move on to the next one? We good? All right, so same variables, but now I'm going to add this additional assumption that air resistance provides a force in the opposite direction of motion proportional to velocity. So the faster the object is moving, we're going to assume that the force of air resistance gets greater, that they are directly proportional to each other. It's actually not a very good model of air resistance, but it works better than no model at all. What we can talk about, in fact, I think one of the groups may explore this in their group project, is actually identifying whether or not a power of velocity is a better measure. Namely, well, I'll just write it off to the side, and then I'll erase it. You don't have to write this down. But instead of saying proportional to v, like the force is kv, maybe it's more like kv to the alpha, where alpha is some number other than 1. Maybe closer to 2, or maybe closer to 1/2. It's proportional to some other constant. And that might vary based on the shape of the object and so forth. There are other models for air resistance that would include a variable for amount of surface area exposed. So the wider the object is, the more air resistance there would be, and it would also depend on velocity as well. But let's just do the simple one, okay? So you've got an object above the ground, two forces now acting on it. First force, same force as before, negative mg. And now another force acting in the opposite direction, which is proportional to velocity.
Did you say you're gonna model this one the opposite way?
Sure, why not? I think, yeah, we'll do this to match what's in the book on this one. Oh, I just erased my box. Let's say now, for fun, orient positive as downward. And I think that's because the equations in the book for this particular model, that's exactly what he does. So you may see this in your homework, and it talks about it being oriented downward. This way your equations will match what's actually in there. All right, so now if downward is positive, that's a positive mg, and up would then be in the opposite direction, right? But it's proportional to velocity. So notice if you're going down in a positive way, that your velocity's down, then what direction is the force of air resistance acting? In the negative of that, right? So upward, I would write this as negative kV. And the k comes from this word proportional, right? Whenever we say something is proportional to another variable, we write it as k times that variable. Constant proportionality, that's from your algebra. Okay, so again, we're going to set ma equal to the sum of all the forces. So that's m times the second derivative. Oh, that's s. Is equal to, now we've got mg going down, positive, minus kv. But what is v?
ds dt.
Yeah, it's that first derivative, which I will, just to be consistent, write it as ds dt instead of s prime.
And do we necessarily have to put the d squared as dt squared, or do
S double prime is fine.
Yeah.
Yeah. If you wrote it as ms double prime equals mg minus ks prime. Works just as well. I just have a habit. I don't know why.
MG or MG?
M for mass. Oh, so over here that's an M.
I thought you said NG over here on the
Oh,
last side.
Now, if I divide everything through by m, I'm going to actually write this in its linear form. What you end up with is this equation right here. Divide through by m, and I'm going to move the k ds dt to the other side. I end up with second derivative s with respect to t minus, now plus actually, k over m ds dt equals mg. What I mean when I say I'm writing that in its linear form, remember, to be a linear differential equation, you have to be linear with respect to the derivatives of your dependent variable. Oh, and the m should be gone. Yes, those of you that are squinting at my m over here. You're correct.
But there should still be an m under the k.
Yes, because if I divide everything through here by m,
Right.
m, these are gone. These are gone. And if you did an initial value problem, you'd also have to put in those initial conditions. Okay.
Which would give you the answer for k.
Well, the initial conditions will give you the C's that show up in the solution. To find K, you're going to have some additional information provided about the particular model. And that K will typically have to do with the shape of the object, or they'll tell you that they know the amount of resistance at a given time or at a given velocity. So if you're expected to find K, you would need one more source of information, one more data point that tells you in one of the conditions that you have all the variables except K. Okay, so that happens, and you'll see that in some examples, but you're able to figure that out. That's just algebra again. They give you all of the variables except one. You find the one that you're missing. As time goes by, we will refine models in this section, and we'll also introduce some other models. There are some other models already in section 1.3 that you're welcome to go through and read about. They may be more relevant to things you're interested in. There's some chemistry, reaction models, chemical reaction models that are in this section that I didn't include. I can't remember if I left anything else out. Let me just introduce a term that's going to be used. You may see this in the book, and I just want you to be familiar with it. The term of dynamical system is basically a system that depends on time. A dynamical system is a system that changes or evolves as time passes. So a dynamical system, in fact, that's a common course you take as a graduate in engineering programs, dynamical systems. And there are some pretty interesting software packages that will model these things with feedback loops and all kinds of interesting ways of modeling these state diagrams for dynamical systems. Just know that all I mean by dynamical system in the context of this class, differential equation that depends on t. That's what a dynamical system are. So the time variable is t. Their other variables are often called state variables because they indicate the state at which the system is in at any given time t. So if I talk about the state of the system, that means what is the set of values for variables at a given time t. And the solution for a dynamical system is often called the response of the system. And here's just, this model right here happens to be the radioactive decay model or the population dynamics model. The state variable is A. The response of the system is the solution to that differential equation, which happens to be given there for you. And any systems that are not dynamical are called static systems. So all of the models that we talked about in this section are dynamical systems, whereas systems that don't evolve over time but just change based on what different variables are involved in the model. We won't do a lot of those types of examples, so we can typically think mostly in terms of dynamical systems in this class. All right, I'm going to stop the recording there.